Hi, my name is Samuel Staus, and I will be doing my final exam. So this is my Bearcat card, and as you can see, the M number is going to be M123403336. So thank you. All right, now moving on to question one. So question one states, in this study, two independent random samples with a interval/ratio data were collected. In group one, a random sample of 133 primary hypertension patients were taken, and each person's total cholesterol, which was measured in milligrams, I don't know what the /DL is, was recorded. Excuse me. In group two, a random sample of 41 normotensive shortened for NT, was taken, and their total cholesterol was recorded as well. So using the 5-step hypothesis testing process to check if the pH group's population average of total cholesterol level is significantly larger than 210 milligrams. So we're going to use alpha as 5%. So first off, what we're going to have to do is we're going to have to state our hypothesis and identify our claim. So the first hypothesis, our real hypothesis, is going to be mu equals 210 milligrams. So we're not going to claim that. Now we're going to use our null hypothesis, which is going to be mu is greater than 210 milligrams, and we're going to claim this hypothesis. So after claiming the null hypothesis, we're going to find our critical value. So to find our critical value, since the hypothesis subpart 0, mu would equal k, and the null hypothesis h subpart 1, mu would be greater than k. So since it's a one-tailed test, and alpha is 5%, so 0.05, our critical value is going to come out to 1.65 using the table. So after we find our critical value, we're going to have to compute our test value. So using the test value equation, so z equals the mean minus mu divided by the standard deviation, so omega, divided by the square root of our sample size, so n. So if we get all of our data here, so the mean is going to be, so we're going to use pH mean, so 214.71 minus mu, so 210. If we take that 210, so 210 significantly higher, that's going to be our mu, and 29.66 is our standard deviation. So in order to find that, since we are given only population variance, we're going to do we're going to take the square root of our population variance in order to get our standard deviation. So it's going to be 29.66. So putting that there, and then our sample size, so we already read random sample of 133, so that's going to be our n. If we compute all that together, z, so our test value will come out to 1.83. Now, after we find our test value, we're going to have to make our decision. So since 1.83 is just beyond 1.65, we're going to reject the hypothesis. We're going to reject this because there is enough evidence to support a claim. So that is question number one. Now, going down to question number two. So question number two is kind of similar to the last question. So two independent random samples with interval ratio data were collected. In group one, a random sample of 133 primary hypertension patients were taken, and each person's total cholesterol measured in milligrams was recorded. In group two, a random sample of 41 normotensive patients was taken, and their total cholesterol was also recorded. So part one of question two asks, what is the point estimate of the primary hypertension patient's total cholesterol? So the point estimate of the primary hypertension patient's total cholesterol basically is its mean. So the mean is 214.71 as stated from the pH level, so sample mean. Now, part two asked, find the standard of error of the sample mean of the primary hypertension patient's total cholesterol. So So in order to find the standard of error of the sample mean, what we're going to do is we're going to take the standard of error equation. So that's going to be omega subpart the mean equals omega divided by the square root of n. So given that our standard deviation, or omega, is 29.66, and the random sample is our n, so 133. So the standard of error that we find after calculating that is 2.57. So that's going to be our standard error of the sample mean. Now, part 3 asks, can we apply the central limit theorem to estimate the population mean? Well, yes. So we can apply the central limit theorem in order to estimate our population mean of the primary hypertension patients, because the patient's total cholesterol, because the given sample size is greater than 30, from a population. So yes, we can apply the central limit theorem. Now, part 4 asks, find a 90% confidence interval of the population mean of the primary hypertension patient's total cholesterol. Also, interpret its meaning. So, in order to find the 90% confidence level of the population mean, we're going to take our confidence level equation. So it's going to be the mean minus z, so our test value, times omega divided by the square root of n, which is going to be less than mu, and then mu is going to be greater than the mean plus the test value times omega divided by the square root of n. And if we put all of that information together, which we just had, so it's going to be 214.71, which we just got from our mean. The test value is going to be 1.65. And then from the table, so the standard deviation is 29.66 divided by our sample mean. Moving this ahead, sorry. And then doing that vice versa on the other side by adding an addition symbol opposed to a subtraction symbol. So after we do all of the math inside, so we do 29.66 divided by the square root of 133 times that by negative 1.65, and then we add 214.71. And then on the right side, on the left side, that will come out to 210.47. Now on the right side, 214, first off, what you do is just exactly on what you did on the left side. So the standard deviation divided by the sample size, the square root of the sample size, times that by our test value, so 1.65, and then adding that to 214.71. So that will come out to 218.95. Now, after we get our values, so to interpret this, one can be 90% confident that the population mean between 210.71 and 218.95, just in between these two values, is based on a sample of 133 patients. So we can be 90% confident that the true population mean is between these two numbers. Now, going on to question number 3. So question number 3 is going to be a chi-square test. Sorry if I butchered that pronunciation of that. So using the chi test of independence to our example, we have as a random sample of 500 adults who are questioned regarding their political affiliation and opinion on the tax reform bill. We will test if the political affiliation and their opinion on tax reform bill are dependent at a 5% level of significance. So part 1 of question number 3 asks, describe the type of relationship between political affiliation and opinion on tax reform. So the type of relationship between political affiliation and opinion on tax reform is dependent. So because we claim that we are testing the dependent hypothesis. So what we're going to do, so that's part 1, and then moving on to part 2, calculate the chi-squared statistic and check the independency of the two variables, political affiliation and opinion on tax reform. So using alpha equals 1%. So, just like the last two questions, we're going to take two hypotheses. So our actual hypothesis, opinion on tax reform, is independent of political affiliation. Excuse me. And our null hypothesis, tax reform is dependent of the political affiliation. So we're going to claim our null hypothesis because of the relationship that we interpreted in part 1. So using our calculator, going through the steps that we learned through the homework, we can calculate that our p-value is going to equal 0.00015. So after calculating this p-value, we can then interpret that the null hypothesis, the one that we claimed, will be rejected because the p-value is less than 0.01. But there is enough evidence to support the claim that the opinion on tax reform is dependent of political affiliation. So, moving on to question number 4. Question number 4 involves, so what we're going to do, correlation coefficients. So a small sample study is conducted involving 15 infants to investigate the association between gestational ages at birth X and measured in weeks and birth weight, which is Y. And then these are all measured in grams. So the first part of question 4 is calculating the Pearson sample correlation coefficient R and interpret its meaning. So what we're going to do is we're going to find both our X and Y values. So what we're going to do is we're going to take the sum of the gestational weeks, which is X. So finding, and also our Y value, so the sum of the birth weight as well, and getting the mean from both. And then next, what we're going to do is we're going to take the sum of the squares, so X, and also the sum of the products, which is SSY. Now, moving on, finding all of these values, we're going to combine X and Y. So there's 15, so the sample size, so there's 15 infants. So we're going to use N as 15. And now we're going to use using this as our X and Y. So X and Y combined. So we're going to take X minus the mean of X times that by Y minus the mean of Y. We're going to get 28,993.46. So now that we have all these values of the X, Y, and also the X and Y combined, we're going to find our R value. So using the R value calculation, so it's going to be the sum of X minus the mean of Y times Y minus the mean of X. This will, and then divide that by the sum of the products and also the sum of the squares. So we put all of our values in. We get since we already combined X and Y together, we're going to put our value into there. Divide that by the square root of sum of the products and times that by the sum of the squares. So times that together. Times that together, taking the square root of that, doing that on the calculator, and dividing 28,993.46 divided that by that value that we calculated here. Our R value comes out to 0.87. So after we find that, to interpret its meaning, we now see that there is a strong positive correlation, which means high X goes with high Y scores. So basically on a chart, it's going to be in a high positive correlation up top. So now moving on to part 2. So testing the hypothesis. So the first hypothesis. So P subpart XY equals 0 for the right tail alternative at 5% the significance level. So since since P sub part 0 equals 0, the null hypothesis H sub part 1 is going to be not equal to 0. So we're going to take, so we're going to claim the null hypothesis, and what we're going to use is we're going to use table F. We're going to find T using the degrees of freedom. So using that table, we come out to 6.647. So the degrees of freedom, and then alpha is going to be 5%, which will then equal 1.771. This is going to be our p-value. So since our t-test falls within the critical value, or the critical region, I'm sorry, we reject the null hypothesis. We're going to reject the null hypothesis. So moving on to part 3. Part 3 states, fit the line of best fit of x on of y on x, and then use this model to estimate y when x equals 18 weeks. So we're going to use the regression equation. Which would equal y equals a plus bx, or you can do bx plus a. So taking the sum of I don't know why it's not focusing, of x and the sum of y, just like we did in part 2, we are going to find, and also the mean of x and y, and the sum of the squares, sum of the products. So in order to find b, we're going to take our sum of the products, divide that by the sum of the squares. So b would equal 182.147. In order to find a, we're going to take our mean of y minus b times, or minus the bracketed together, so b times 38.36, so that's going to be our mean of x. So a is going to be negative 4,010.566. So then, using the regression equation altogether, y equals 182.147 times, or x minus 4,010.566. So when x would equal 33, so if we plug 33 into x, y will come out as 2,000.29. So that is part 3, and that will be it. Thank you.